Hello and welcome back. In the last video, I gave a quick introduction to what linear models are, how they work, and different ways you can interpret information based off of them. This video is going to cover linear regression. Just linear regression, nothing else, nothing more, in as little bit of time and as much detail as possible. So linear regression is also referred to as least squares regression, and the objective of this is to minimize the MSE, which stands for, so it's right up here, mean squared error, right? This means you will take the error, you will square it, that's usually just to make sure it's a positive number, and take the average of it, right? The purpose of that is because, error is not something we want in our models, and we want to minimize it because, well, if we don't want error, then we should try to minimize it as much as possible. And if we're talking error, that is referring to the difference between the predictions, that's an eraser, and the true value, right? What do those mean again? Just a quick refresher. Predictions are the outputs of our model. Our model learns off of some amount of data, and we want it to be able to predict off of new data. That makes a prediction. The true value, again, we have training data, meaning that we have data with different features, but we also know the results of those features or the classes they belong to, right? We make a comparison between the true value and the predictions. That gives us the error, because if our prediction is off by a certain amount, that means that we have some error, okay? So we take the error between the prediction and true value of all of our data points, all of our predictions. We sum that together, square it, and then take the mean or average of it. And that should give us one number. That will give us the mean squared error, and we can iteratively train our machine learning model to minimize that. Okay? So there are some things to consider about it. Is that because this is a very simple algorithm, you don't have much control over model complexity. Okay, so let's put just a little bit of an equation out here. If you saw the linear models video, you'll remember that our model is represented with this equation. Y hat represents our prediction, while our prediction is equal to our weight matrix multiplied by our feature values or input data plus any kind of bias or offset that we're working with. Okay, this is going to give us a prediction value. Remember that. There is a true value, we'll call it Y true, that is just the ground truth. It's a value associated with our input data points, right? We compare the prediction with that Y true value, and again, that's how we give our mean squared error. But you can see this equation is very simple, and although we're trying to calculate this mean squared error, it doesn't have any presence inside this equation whatsoever, right? It has no control over the model. It just really tells us when to stop, when to kind of call it quits, and then take our model as something that we can take out into the world and make new predictions based off of. So that's why we say it doesn't have control over model complexity, because it's really just not a part of the model. But the benefit of this is that it makes our model less likely to overfit, because our model isn't learning mean squared error, right? We're using mean squared error as a metric to train our model, but it does not actually define the model in any way. So first, this applies primarily to smaller data sets, and check out the video comparing linear regression to ridge regression, which we'll talk about in another video, and this will become easier to understand.